Look up tonight. You see it? That cold, silent sphere hanging in the blackness. The moon. We take it for granted. It's just there. A big round lamp in the sky. We know the basics. It causes tides. It lights up the dark, and we even sent people there. But what if it wasn't just a lamp? What if it was the invisible anchor holding our entire world together? Now, I want you to ask yourself this. What if, in one impossible sudden moment, the moon was gone? Instantly. Not exploded, not drifted away slowly, but simply vanished. Poof! The immediate changes would hit us with terrifying speed. We might think the sun runs our world, but there is another cosmic dance happening every second, a fight between gravity and water that the moon controls completely. If you thought the lack of nightlight would be the only problem, you are missing the biggest point entirely. The first thing you notice wouldn't be silence in the sky, it would be chaos on the planet. Our oceans are massive. They are always moving, driven by two things: the gravity of the sun and the much stronger, closer gravity of the moon. Think about how tides work. They aren't just gentle waves rolling in, they are the entire ocean pulling itself outward toward the moon, creating those high water levels on the side of the Earth facing the moon and also on the side facing away from it. This immense pull, this stretching of water, is a constant reminder of the moon's power. It's an enormous effect, much bigger than the sun's tidal pull, simply because the moon is so much closer to us than the sun is. If the moon disappeared, the dominant tidal force would be immediately removed. The oceanic rhythm, which has kept the flow of currents predictable for billions of years, would shatter. First, you would see a massive, immediate change in water levels everywhere. Ocean levels would rapidly seek a new equilibrium, governed only by the sun's weaker, smaller pull. The sun still causes tides, but they are only about half as strong as the lunar tides. The huge daily high tides and low tides would be replaced by much smaller, gentler solar tides. But the biggest danger isn't the smaller waves. It is the immediate, chaotic energy release of the water that was just moments ago obeying the moon's command. That water has enormous stored energy. That energy doesn't just disappear. The water masses that were just being pulled around would crash back, generating worldwide mega tsunamis unlike anything history has recorded. Coastal regions, low-lying cities, and everything within miles of the shore would be wiped clean. This wouldn't be localized. This would be a global, immediate flood, as the ocean's inertia reacted violently to the sudden loss of its dominant gravitational partner. And it wouldn't stop there. The moon's disappearance would not just affect the surface water, it would shatter the deep oceanic systems that rely on tides to move. The Great Ocean Conveyor Belt, the vast system of currents that transports heat and nutrients around the globe, relies on tidal mixing to start its engine. Without the massive lunar pull driving that mixing, deep ocean currents would seize up, leading to profound long-term consequences for sea life and, eventually, for global weather systems. But water is only one part of the equation. What about the solid Earth itself? That is where the real threat to our planetary stability begins. You see, the moon doesn't just pull the water, it pulls the ground beneath your feet. It literally stretches the Earth, creating solid Earth tides. If that anchor vanishes, the result is planetary motion spinning wildly out of control. If the tides collapsing wasn't enough to make Earth uninhabitable, the moon's disappearance ensures it. Its next effect hits the core structure of our world, the angle at which we spin. The moon is incredibly important because it acts like a giant steadying gyroscope for Earth. It keeps our planet's axial tilt, that 23.5-degree angle that gives us seasons, remarkably stable. Without the moon's gravitational influence locking that axis in place, Earth's axis wobbling would start to wander wildly. This isn't an instant wobble, but rather a slow, terrifying drift. However, even a small, unexpected change in the axial tilt causes catastrophic climate instability over a relatively short period. Ask yourself this: what happens if the axial tilt shifts radically? If the tilt were to move towards 0 degrees, the equator would get constant sunlight, while the poles would plunge into perpetual twilight. Seasons, as we know them, would vanish. Imagine perpetual summer at the center of the planet and perpetual winter at the extremes. If the tilt moved toward 90 degrees, every location on Earth, even the equator, would swing wildly between extreme summer days and extreme winter nights. One half of the year, a spot would face the sun directly for months, baking everything. The other half of the year, that same spot would face perpetual blackness, freezing everything solid. Without the moon fighting against the gravitational tugs from the larger planets in the solar system, especially Jupiter and Saturn, Earth's axial stability is compromised. Over thousands of years, this uncontrolled Earth's axis wobbling would result in chaotic climate shifts, making sustained life impossible anywhere on the globe. We rely on that steady 23.5-degree angle to keep our water liquid and our climates balanced. Lose the moon and you lose the guarantee of that stability. Now let's talk about the speed of rotation, the length of day shifting. The moon is currently slowing Earth's rotation down. This happens because of the friction generated by the tides. The water trying to follow the moon drags against the ocean floor, acting like a planetary brake pad. This is why, over geological time, our days have gotten longer. When the Earth was young, a day lasted maybe 6 hours. Right now it's 24 hours. If the moon vanishes, this braking effect instantly stops. More than that, the immense amount of rotational energy that the moon was managing is suddenly released. Over the short term, meaning the first few hours, the immediate release of rotational energy wouldn't suddenly make the day 1 hour long, but the length of day would start to quickly decrease. Scientists estimate that if the moon disappeared, the day would shorten significantly over a few million years. The steady slowing process we rely on for global equilibrium would be gone. Within the first year, Earth's rotation would start to speed up noticeably faster than it is now, shrinking the hours in a day. Imagine trying to adapt to a 20-hour day or even shorter. This massive length of day shifting would trigger extreme wind patterns and changes to the atmosphere. The speed of rotation plays a central role in creating our global weather destabilizing systems. If the day gets significantly shorter, the massive Coriolis forces that shape hurricanes and high-speed jet streams would intensify exponentially. Wind speeds would soar, creating perpetual superstorms. The planet would become a non-stop tempest. The destruction of the oceans and the chaos in the atmosphere would instantly ruin surface life. But the creatures that survive rely on something else entirely, instinct guided by the cosmos. The catastrophic changes to water and weather are threats we understand through physics. But the moon's disappearance would also trigger an immediate breakdown in the biological world, relying on an invisible cosmic clock. Let's first look at the most obvious change for any survivors. Night sky brightness changes. The moon is easily the brightest object in our night sky. It outshines the next brightest star, Sirius, by an enormous factor. Its light is so strong that it has created conditions where many species have adapted to lunar light cycles, especially during the full phase. If the moon is gone, the night sky plunges into pure, star-dominated darkness. For astronomers, this would be amazing. No more moonlight washing out the view of distant galaxies. It would suddenly become possible to see the entire Milky Way, even in relatively dark regions with incredible clarity. The distant stars would appear sharper and more defined, creating a spectacular, never-ending display of the cosmos. But for the rest of Earth, this deep darkness is a problem. Many nocturnal predators and migratory animals rely on the moon's light for navigation, hunting, and mating. Losing that main light source means a sudden, acute crisis for everything that lives in the dark. This leads directly to animal behavior disruption. The lunar cycle dictates the biological clock for millions of creatures. Marine life especially times its reproduction based on the moon, synchronizing mating rituals with lunar phases that influence the highest tides. Without the lunar pull, the biological triggers would vanish, disrupting critical breeding cycles immediately. Imagine creatures that use the moon's angle for navigation, like sea turtles or migratory birds. They depend on the consistent light source to maintain their course. When the moon disappears, that navigational signal is lost. They would become disoriented, leading to mass mortality events for species mid-migration or attempting to reproduce. Terrestrial animals are also affected. Nocturnal hunters, from owls to big cats, would struggle with the plunge into total darkness. Their hunting strategies rely on shadows and light levels that the moon carefully controls. The entire nocturnal food web would suffer a sudden, violent imbalance. Furthermore, the moon and its gravitational pull affect everything from human sleep patterns to plant growth cycles. The consistency of the 28-day lunar cycle maintains the delicate equilibrium between countless interacting biological processes. When that consistent force is removed, animal behavior disruption becomes absolute chaos. Species that depend on the lunar phase for emergence, hibernation signaling, or foraging would miss their cues entirely. We now know the immediate physical devastation, water and wobble, and the biological chaos, darkness and instinct. But how do these short-term shocks translate into a long-term, irreversible collapse of the global environment? We need to understand the slow, final death blow, the complete change to global temperatures and environment, ensuring that nothing returns to normal. The initial physical and biological shocks caused by the moon's disappearance would eliminate most complex life swiftly. But the long-term changes, particularly the long-term climate impact, guarantee that the planet remains hostile and unstable forever. We already established that the Earth's axial wobble would destroy the stability of the seasons over millennia. However, the loss of tides and the resulting breakdown of oceanic currents initiates a destructive process much faster. The key component of global climate stability is the immense distribution of heat managed by the ocean. Warm water moves from the equator toward the poles, releasing heat, and then cold water cycles back toward the equator. This acts like a giant temperature regulator for the entire planet. If the deep ocean mixing that lunar tides provide collapses, the oceans would begin to stratify. Layers of warm and cold water would stop mixing. This disruption of the major ocean currents, sometimes called the global conveyor belt, would lead to massive, unpredictable temperature swings globally. Regions that depend on warm currents, like Western Europe reliant on the Gulf Stream, would rapidly plunge into deep freezes, leading to a swift, catastrophic long-term climate impact. Meanwhile, equatorial regions might overheat uncontrollably as ocean circulation stops carrying heat away efficiently. The entire climate system, currently balanced between atmosphere and ocean, would break down into extremes. The overall consequence is irreversible glaciation and desertification. The planet would be carved up into regions of permanent, freezing tundra and massive baking deserts, all separated by perpetual violent storms caused by the accelerating planetary rotation, which we discussed earlier. Without the moon's calming presence, the planetary system defaults to high-energy chaos. Now let's consider the effects on human infrastructure that tries to escape this impending doom. Effects on space travel and satellites. While the surface descends into chaos, human activity beyond Earth is also immediately compromised. Our current space infrastructure, the International Space Station, communication satellites, and navigation systems all rely on stable orbits and precise timing dictated by Earth's known gravitational field. The Moon exerts a subtle but definite gravitational force on objects in Earth orbit. Satellites and the ISS orbit Earth at speeds of thousands of miles per hour. Their trajectories are calculated using incredibly precise models that account for the gravity of the Earth, the Sun, and yes, the Moon. If the Moon suddenly vanishes, every single object currently in orbit would instantly experience a small but significant shift in its gravitational environment. This unexpected shift means that the orbital paths of satellites, the ISS and space debris would suddenly become unpredictable. The subtle effects on space travel and satellites would compound quickly. Satellites relying on precise positioning, like GPS or communication networks, would begin to drift off course, requiring constant, expensive course corrections that few have the fuel capacity for. The ISS, while robust, would face the same unexpected orbital shift, possibly requiring immediate, unscheduled maneuvers to maintain its safety. The entire framework of stable low Earth orbit navigation is disrupted. When do these compounding factors, from the flooding to the orbital collapse, make Earth fully uninhabitable, ensuring the total end of the current ecosystem? We need to calculate the speed of our destruction to know how much time, if any, we would have left. We have charted the cascading failures, global mega-tsunamis, accelerating rotation, planetary axis instability, the collapse of global oceanic currents, and orbital infrastructure failure. So, how fast Earth becomes uninhabitable is a question of measuring the speed of those catastrophic events. The short answer: extinction starts immediately, but the complete physical destruction occurs across three main phases. Phase 1. The first hours, the watery death. The instantaneous loss of the Moon's tidal influence would release the massive inertia stored in the oceans. This results in global mega-tsunamis slamming into coastlines and low-lying continental shelves worldwide. Simultaneously, tidal forces disappear, destroying the daily rhythm of billions of marine and coastal creatures. Within this phase, mass die-offs and immediate infrastructural collapse occur across the planet's most populated regions. This immediate flood ensures that organized civilization ends swiftly. Phase 2. The first decade, the atmospheric whiplash. The planet's rotation begins its noticeable, steady acceleration. This change in speed, coupled with the collapse of the major warm, cold ocean currents, drastically increases Coriolis forces. This results in weather destabilizing entirely. Perpetual high-energy superstorms, winds blowing faster and more violently than anything currently known, would constantly scour the planet's surface. These winds would accelerate desertification in continental interiors and ensure that remaining settled areas are crushed by atmospheric violence. Any surviving structures or groups would face continuous atmospheric assault. Phase 3. The long drift, the planetary death sentence. This phase is governed by the gradual, relentless Earth's axis wobbling. Without the lunar stabilizer, the gravitational influence of Jupiter and Saturn would slowly increase the chaotic drift of Earth's axial tilt. Over a period of hundreds to thousands of years, the axial tilt would swing wildly, resulting in unimaginable climate extremes. Periods of perpetual baking sunlight followed by long, crushing freezes would alternate across the planet's surface, sterilizing the remaining habitable zones. The planet does not explode. It does not fly into the sun. It simply defaults to a non-life-sustaining state. How fast Earth becomes uninhabitable depends on which threshold you cross first. The destruction of civilization by water, hours, the collapse of weather systems, years, or the final climatic sterilization, centuries to millennia. For humans, the window closes in hours. For complex ecosystems, the death process is guaranteed within decades. The Moon is not just a pretty neighbor, it is the silent gravitational guardian that allows us to exist, maintaining the critical water, weather, and axial stability that define life on this planet. Its sudden removal is a planetary death sentence, executed by the very forces that currently sustain us. We spent this time focused on one impossible scenario, the abrupt loss of our planetary anchor. But the principles of cosmic forces and planetary dynamics that we use to track Earth's fate are based on the same rules that govern everything from the smallest neutron star to the largest galaxy cluster. The study of catastrophic events, whether sudden or slow, relies on understanding the fundamental forces: gravity, electromagnetism, and the odd mechanics of matter itself. For instance, much of the research happening in modern space science, from designing systems for the International Space Station to hunting for black holes, requires measuring extreme forces and precise timing. When researchers look for black holes, they are looking for their gravitational effects on surrounding matter, similar to how we analyze the Moon's stabilizing effect on Earth. A supermassive black hole at a galaxy's center is invisible, but its immense mass reveals itself by the frantic, fast orbits of stars around it. That orbital motion tells scientists the mass of the hidden object. The idea is the same. Gravity is the invisible hand controlling the action. The International Space Station itself is constantly dealing with the subtle, complex physics of orbital movement. Because objects in orbit travel incredibly fast, every movement must be precisely calculated, accounting for the gravitational pulls around them. This is why the precise balance maintained by our Moon's presence is so essential, even for satellites far above us. When science tries to map the universe, whether it is plotting the speed of planetary rotation or calculating the collapse of global weather systems, it all comes back to how matter and energy behave. The cosmos is filled with violence and creation, but everything adheres to a strict set of rules. This chaotic scenario of the Moon vanishing reminds us that stability is often a matter of delicate, large-scale balance. Losing one major piece of that gravitational system triggers a cascading failure that quickly pushes a habitable world into a state of permanent instability. It is the sudden stop of a clock that has kept time for billions of years, and the universe does not offer replacement parts. The precision required to understand even the immediate fallout of the moon vanishing is a testament to how complex our neighborhood is. Researchers developing new instruments like the James Webb Space Telescope or advanced X-ray observatories spend years ensuring their devices can capture the subtle, energetic processes occurring light years away. This same level of attention must be paid to our own backyard because stability is fragile. If the moon were gone, the ensuing environmental collapse would render Earth unrecognizable. The violence caused by the loss of the stabilizing forces would sweep away the ecosystems we know and love, leaving behind a scarred, storm-swept marble spinning too fast on a drunkenly wobbling axis. It's a powerful lesson in cosmic dependence. The analysis of planetary catastrophe, like predicting the immediate effects of losing the moon, demonstrates that even seemingly subtle influences maintain vast systems. The moon's gravity, often perceived only through the gentle rise and fall of the ocean edge, controls the fundamental speed, tilt, and internal fluid dynamics of our entire world. When we look at the deep history of astronomical observations, from the first discovery of quasars, powered by extremely efficient gravity-fed black holes, to the discovery of supermassive black holes lurking silently in our own Milky Way, the constant theme is the governing force of gravity. Without that force, chaos begins. If you want to understand space, like a NASA-level analyst quick without studying for years or paying thousands for a university degree, we have a community that will help you. Link is below. But the moon's disappearance is ultimately science fiction, based on an impossible premise. For a true view of unavoidable cosmic destruction, a scenario written not by sudden, impossible vanishing, but by the relentless, cold laws of thermodynamics, we must look to the ultimate fate of all structure, energy, and life in the cosmos. If you are ready to see how the universe will really end, when the last fires of existence are extinguished and even the toughest gravitational prisons surrender to the cold, click here to this video, How the Universe Will Really End video. I'll see you there.